In this video, we are going to investigate the law that governs buoyancy force, Archimedes' principle. The goal of this video is to determine the relation buoyancy has with an object's density and its gravitational force. So let's get started. Here we have the formula for buoyancy force. It states that the buoyancy an object experiences is equal to the density of the surrounding fluid times the submerged volume of the object and the acceleration of gravity. Through the course of this video, we will see how this equation equates to the words of Archimedes, who states the buoyancy force experienced by an object in a fluid is equal to the weight of the fluid displaced by the object. Have you ever wondered why an object floats in a fluid? You've probably heard that it has to do with the object being less dense than the surrounding fluid. Let's take a look into why that is and determine its relation to Archimedes' principle. An object floats when the force of gravity on the object does not exceed the force of buoyancy on the object. This is due to the fluid having a higher density, containing more mass and thus more weight in the same amount of volume that the object occupies. If we were to increase the density of the object, we would see that there would be a proportional increase in the force of gravity, which is now greater than the buoyancy force that remained the same, causing the object to sink. Thus, an object only floats once the amount of water it displaces has the same mass as the entire object. Let's take a closer look into the limiting factors that allow an object to float. Recall from the previous slide that in order for an object to float, its buoyancy force must equal the force of gravity. By elaborating on the equation for buoyancy, we can prove Archimedes' principle. Setting buoyancy and gravitational force equal once more, we can see that the mass of the displaced fluid must equal the mass of the entire object for the object to float. Now let's consider the percentage of the object that must be submerged in order for the object to float. As it turns out, the percentage of the object submerged when its mass equals the amount of fluid it displaces is equal to the ratio of the object's density and the fluid's density. This is known as the specific gravity of the object. Let's consider the parameters of specific gravity and learn how to use it so that we can determine if something will sink or float. If the specific gravity was less than or equal to 1, the object was able to displace enough fluid to keep itself afloat, implying that even 100% of the object can be submerged and float. Yet, if the specific gravity is greater than 1, not even the entire volume of the object could displace enough fluid, and so it sinks. Now let's begin to actually apply Archimedes' principle. Below is a sphere with the following properties. Dropping the sphere into the water below displaces some of the water. As the sphere is less dense than the water, it will float. Let's suppose that while the sphere floats, only half of its volume is actually submerged, and thus only water equal to half the volume of the sphere is displaced. Assuming the fluid is water, and knowing that the density of water is 997 kilograms per meters cubed, we can now multiply it by half the volume of the sphere and the acceleration due to gravity to calculate the buoyancy force. Performing this calculation yields a buoyancy force equal to the gravitational force, thus confirming the object floats. For this next scenario, I would like to mention that this method could be used on objects of abstract geometry, but for simplicity, we're going to use a sphere again. Let's suppose that we have the same sphere as in example 1, but for the sake of the example, we lack the knowledge to determine its volume. If we wish to only use its submerged volume to determine buoyancy, we can design an apparatus that allows us to collect the water displaced by the sphere, as this will be equal to the submerged volume of the object. This apparatus also permits us to obtain the mass of the displaced fluid. By taking information we obtained from the fluid in the beaker, we can represent the density of the water as shown. Notice that because the volume of the water displaced was equal to the submerged volume of the object, these two terms cancel out, leaving just the water's mass and acceleration of gravity. Thus, the buoyancy calculation is just the weight of the displaced fluid. Lo and behold, we find this answer to be the same as scenario 1's, where the object's buoyancy force is once again equal to its gravitational force. Now let's consider a sphere with the same volume but greater density. Notice that this increase in density will increase the force of gravity acting on the object as well. This time, when we place the sphere in the water, the shift in forces will cause the sphere to entirely submerge itself. Thus, the fluid displaced is equal to the entire volume of the object, and at no point did the mass of the water displaced by the sphere equal that of the entire sphere. Proceeding with the calculation and substituting in all known values results in a buoyancy force less than that of the gravitational force. This supports the concept that denser variants of geometric figures that float may not float, but rather sink. Let's consider a scenario where applying Archimedes' principle allows us to determine the weight limits of a raft. Below is a lily pad, a common hangout spot for frogs. We can use the provided information and a free body diagram to investigate how many frogs it will take to completely submerge the lily pad and begin to make it sink. To determine the weight limits of a raft, let's recall Newton's second law, F equals ma. In this case, we are looking into the limit at which the lily pad is 100% submerged but still floating. As the lily pad is not accelerating, the net force is thus zero. If we can consider our free body diagram from the previous slide, then we can deduce the following equality. Using Archimedes' principle, we can express buoyancy in terms of the weight of the fluid displaced. Expanding the masses in terms of density, we arrive at an expression for some multiple of frogs that equals the difference in the two forces. Because we are looking for an expression in the case where the object is completely submerged and on the verge of sinking, the volume of the fluid displaced and the percentage volume of the lily are equal. Simplifying, we finally arrive at an equation for the raft's weight limits. Using the given information, we find that the pad can hold 99 frogs before it sinks. Archimedes' principle tells us that an object must displace water with mass equal to its own in order for it to float. It is for this reason that balloons rise in the air and ships can remain buoyant in water. Specific gravity is the property responsible for dictating the submerged percentage of an object needed to successfully float. In addition to density, one can always reference free body equalities to see if an object floats. This concludes our theoretical coverage on Archimedes' principle.